Welcome back. In our previous lecture, we established the fundamental principle of infrared spectroscopy. We learned that the molecules absorb infrared radiation and transition into higher vibrational energy state. But that raises an important question. What exactly that vibration look like? What is the molecule physically doing when it's absorbed infrared radiation? That is what we are going to explore today. Today's goal is to visualize molecular motion because when we understand how atoms actually move inside molecules, interpreting IR spectra becomes much easier. Take a look at this chart. This chart represents the landscape of infrared spectroscopy. On the horizontal axis, we have wave number measured in centimeter inverse. As we move from right to left, the energy increases. And what is fascinating is that different functional groups absorb in different region of the spectrum. This means that each region of the IR spectrum correspond to specific types of molecular vibrations. Let's walk through these regions one by one. First, look at the high energy region between roughly 4000 to 2800 centimeter inverse. In this region, we primarily see bonds involving hydrogen atoms, which includes oxygen hydrogen bonds, nitrogen hydrogen bonds, carbon hydrogen bonds. Why do these appear at such high wave numbers? Because hydrogen is extremely light, and in vibrational systems, lighter atoms vibrate at higher frequencies. This is very similar to how light spring oscillates faster than heavy one. Now move slightly down in energy to the region around 2300 to 2100 centimeter inverse. Here we encounter triple bonds. For example, carbon triple bond carbon, carbon triple bond nitrogen. We also see cumulative double bonds such as the functional group nitrogen equals carbon double bond oxygen. These bonds are very stiff and strong, which causes them to vibrate at relatively high frequencies. Now we arrive at one of the most important regions in IR spectroscopy, 1800 to 1500 centimeter inverse region. This area is dominated by double bonds. The most famous example here is carbonyl group. The carbon double bond oxygen stretch is extremely strong and typically appears near 1715 centimeter. This peak is one of the most recognizable signatures in organic spectroscopy. In addition to carbonyl groups, we may also observe vibrations from carbon double bond carbon, carbon double bond nitrogen bonds. Finally, we move into lower energy region below 1500 centimeter inverse. This area contains vibrations from single bonds involving heavier atoms. For example, carbon single bond oxygen, carbon bond X, where X is halogen, that is organometallic bonds. This region is often called as a fingerprint region because the pattern of peaks here is extremely unique for each molecule. But all of this brings us back to a fundamental question. What exactly is happening inside the molecule? How are the atoms moving to produce these absorptions? To answer that, we must understand the type of vibrational motion. So, molecular vibrations can be broadly classified into two fundamental categories, stretching vibrations and bending vibrations. These two types of motion are responsible for nearly everything we observe in and IR spectrum. So let us start with stretching. Imagine a chemical bond as a spring connecting two masses. When two bond when the bond vibrates, the atoms move closer together and farther apart. This means the interatomic distance changes along the axis of the bond. That motion is called stretching vibration. Stretching vibrations can occur in two different ways. The first is symmetric stretching. In this case, identical bonds stretch and contract together at the same time. The motion is balanced and coordinated. Both bonds expand and compress simultaneously. Because the motion is relatively simple and balanced, it is usually requires slightly low energy. The second type is asymmetric stretching. Here, one bond is stretching while the other bond is compressing. The atoms move in opposite direction. This creates a more complex motion. As a result, asymmetric stretching generally occurs at higher frequencies and therefore higher wave numbers. Now let us compare stretching and second category of motion, bending vibrations. Instead of changing the bond length, bending vibrations change the bond angle between atoms. Imagine two bonds connected at a central atom. Instead of stretching, the angle between them opens and closes. That is bending. And here is an important principle. Stretching a bond requires more energy than bending it. Why? Because stretching means pulling atoms apart against their electrostatic attraction that requires significant energy. But bending simply changes the angle between atoms, which is easier. As a result, stretching vibrations appear at higher wave numbers, bending vibrations appear at lower wave numbers. This is very useful rule when interpreting spectra. Now let us look more closely at bending vibrations. Bending vibrations are surprisingly diverse. They can occur within the plane of molecule or outside the plane of molecule. So we classify them into two major types, in plane bending and out of plane bending. First, imagine that a molecule is flying flat on a sheet of paper. Any motion occurring within that plane is called in-plane bending. There are two important types. First is called scissoring. In this motion, two atoms move toward each other and away from each other. The bond angle opens and closes just like a pair of scissors. For CS2 group, this motion is typically appears around 1450 centimeter inverse. The second type is called rocking. Here both atoms move together in same direction, swinging back and forth within the plane. This motion resembles a pendulum. Rocking usually occurs at lower energy, typically around 720 centimeter inverse. Now let us imagine something different. Instead of staying on a paper, the atoms begin to move above and below the plane. These are called out of plane bending vibrations. The first example is wagging. In wagging motion, both atoms move up and down together. They move in phase with each other. The motion resembles a dog wagging its tail. This vibration often appears around 1250 centimeter inverse. The second type is twisting. In twisting motion, one atom moves above the plane while the other moves below the plane. The atoms move in opposite directions. This twisting motion also typically occurs near 1250 centimeter inverse. Now, let us compare these bending vibrations with stretching vibrations. For example, in CH2 group, the symmetric stretching vibrations appear around 2853 centimeter inverse. the asymmetric stretching vibration appears around 2926 cm inverse, but bending vibrations occur much lower, that is scissoring near 1450 cm inverse, rocking near 720 cm inverse. This clearly demonstrates the rule we discussed earlier. Stretching requires significantly more energy than bending. These are various types of vibrations as discussed. Let us summarize what we have learned today. Polyatomic molecules are incredibly dynamic systems. They are not performed just one motion, they are performing many motions simultaneously. At a given moment, molecule may be undergoing symmetric stretching, asymmetric stretching, scissoring, rocking, wagging, or twisting. All of these vibrations occur at the same time. It is almost like a complex molecular dance. Each of these vibration motions correspond to a specific energy, and if vibration produces a change in dipole moment, it will absorb infrared radiation. So every peak in IR spectrum represents a specific molecular motion. By analyzing these peaks carefully, we can reconstruct the structural blueprint of the molecule. So, in this lecture, we explored different types of molecular vibrations. We learned the major regions of the IR spectrum, the difference between stretching and bending vibrations, the concept of symmetric and asymmetric stretching, and four key bending motions: scissoring, rocking, wagging, and twisting. In our next video, we will move one step further. We will examine specific functional groups and learn how their characteristic vibrations allow us to identify molecules instantly in the laboratory. Thank you for watching. I will see you in the next lecture.